Hello fellas and welcome to another video of Epoxy channel. In this video we will explore polysulfide epoxy systems, their unique chemistry, key properties and versatile applications across various industries. This is the fourth video and I hope you enjoy. In recent years, three main classes of mercaptan-terminated polymers have gained attention in various industrial applications. One of the earliest studied reactions was between liquid polysulfide polymers and epoxy resins. This interaction, initially explored by researchers like Fettes and Gannon, revealed that these two polymer types could combine to form materials suitable for casting, coatings, laminates, potting compounds, and adhesives. In many adhesives formulation, epoxy resins serve as the major component, but modifying it with liquid polysulfides often imparts unique chemical and physical properties, which will be discussed in a separate dedicated video. Beyond polysulfide epoxy systems, there are also interesting developments in polysulfide polyether hybrids. For example, polymers have been synthesized with polyoxyl alkane backbones that are terminated with mercaptan groups. This is typically achieved by esterifying polyols with thiosubstituted organic acids. Such polymers can be effectively cured using agents like tetramethyl teuram disulfides and manganese dioxides. Another group of mercaptan-terminated polymers include those derived from polyesters. Scientists have created these by reacting diacrylate-terminated esters with hydrogen sulfide, producing mercaptan-terminated polyesters that can be cured with dicumyl peroxides and magnesium oxide to form rubber-like materials. Additionally, mercaptan-terminated polyesters have been synthesized through reactions between glycols and mercaptan organic acids, further expanding the range of available polyester-based mercaptan polymers. In the field of polyurethanes, researchers have developed polymercaptans, polyurethane polymers by reacting disulfide-containing polyols with diisocyanates and dimercaptans. These polymers cure readily with oxidizing agents. It is also possible to cure mercaptan-terminated urethane prepolymers by capping them with non-polymeric polymercaptans, yielding products such as mercaptan-terminated ureas, thiourethane-linked polyesters, or polyether polyurethanes. Another notable category is polysulfide-terminated olefins. For instance, branched-chain mercaptan-terminated polybutadiene has been prepared by polymerizing polybutadiene with xanthogen disulfide, followed by pyrolysis. Other approaches involve reacting conjugated dienes with sulfur, then hydrogenating the resulting products to obtain low molecular weight polymers bracing mercaptan group. Finally, there are polyester polymercaptans produced by reacting polyols with mercaptogenic acids, followed by oxidation of the resulting prepolymers to create higher molecular weight polymercaptans. These can be cured efficiently with lead dioxides. Polysulfide-based products can be carefully formulated to exhibit either high or low modulus characteristics, depending largely on the choice of polymer, curing system, and other compound ingredients. These sealants are known for their durability across a variety of challenging environments. However, their resistance to heat has its limits. Typically, they perform continuously at temperature below 100 degrees Celsius, though this threshold can vary somewhat depending on the specific formulation used. The unique molecular structure of polysulfides naturally imparts resistance to ultraviolet light, and oxidative degradation. Still, the extent of this resistance is heavily influenced by the formulation details, especially the polymer content. There is extensive evidence showing that the longevity and durability of polysulfide sealants across different applications are closely related to how much polymer is present. This slide focuses on examining various formulations by exploring the component combinations used in polysulfide sealant compounds. Polysulfide adhesives and sealants are valued for their excellent workability, offering a smooth flow and superior electrical insulation alongside effective corrosion protection. These elastomeric compounds cure completely, often at room temperature, though sometimes slightly elevated temperatures are preferred without any volatile emissions. They provide exceptional properties such as the ability to cure underwater, resist harsh chemicals, maintain high dielectric strengths, and deliver increased physical strength. Their performance extends across a wide temperature range, including very low cryogenic temperatures, while also resisting vibration, impact, shock, and thermal cycling. Additionally, these sealants are metal-free and show remarkable long-term resistance to fuels like gasoline, natural gas, kerosene, and crude oil, their derivatives. They are user-friendly with low drippage during application and offer excellent adhesion to both similar and dissimilar substrates. The table here presents 5 different polysulfide-based compounds tailored for various industry needs. Along the left column, you will find the list of components commonly included in these formulations. Across the top, 5 distinct compounds recipes are shown, each corresponding to a specific application. Starting with component 1. These are one-part sealants typically formulated with lower polymer content to ensure better package stability over time. Compound 2 represents building sealants, which generally feature somewhat lower polymer ratios in practical use. Compound 3 covers insulating glass sealants, where a reduced plasticizer content combined with a higher filler load yields the hardness required for such applications. Compound 4 highlights aircraft sealants designed with minimal plasticizer content to reduce extraction by jet fuels, maintaining seal integrity in demanding aerospace environments. Lastly, Compound 5 is a general-purpose casting compound characterized by high plasticizer levels, providing excellent flow properties suited for casting applications. In the next slide, we will explore the specific roles that these different components play in the compounding process, shedding light on how each ingredient contributes to the performance of the final polysulfide sealant product. Originally, polysulfide rubbers, often called thiocol, were solid materials with very high sulfur content. Early development treated these materials similarly to other rubbers, curing them with sulfur and zinc oxide. However, the introduction of a liquid polysulfide polymer in the 1940s expanded the possibilities for curing agents and accelerated their commercial use. Liquid polysulfide polymers can be cured by a variety of compounds through different reaction mechanisms. The most common curing system involves the oxidation of the thiol terminal groups by metal peroxides. Additionally, other reactions such as adhesion and substitution can occur with the diverse products including epoxy resins, isocyanates, acrylics, and anhydrides. Over time, a wide range of materials has been identified that effectively cure polysulfide polymers. The primary curing agents are metal peroxides and metal oxysalts, which exploit the reducing nature of the thiol groups to promote cross-linking. Examples include lead dioxides, manganese dioxides, calcium peroxides, barium peroxides, sodium and zinc compounds, as well as chlorates, dichromates, and permanganates. Organic peroxides and hydroperoxide have also been used commercially, with many other agents explored experimentally. For most two-part building sealants and casting compounds, a technical grade of lead dioxide is the curing agent of the choice. To control the cure rate, stearic acid is added as a retarder within the curing paste, which typically consists of 50% lead dioxide, 45% plasticizer, and 5% stearic acids. Manganese dioxide is used as the curing agent in insulating glass sealants. It offers better UV resistance through glass and maintains adhesion over extended periods. To accelerate the cure, a base is added, providing about 30 minutes of working time and a full cure in roughly 8 hours. One-part sealants commonly use calcium peroxide as the curing agent because it remains inert in the absence of moisture. Barium oxide is included as a dehydrating agent just before adding the calcium peroxide paste. This helps the package stay stable by absorbing water molecules. In aircraft sealants, inorganic chromates have been employed to improve heat resistance. Some manganese compounds have also found use in these demanding applications. Cumin hyperoxide has also been applied in few casting compounds, but it is avoided in the building sealants due to its negative effect on adhesion. Now let's look at the role of fillers in polysulfide compounding. Carbon black is primarily used in aircraft-grade compounds. It contributes to higher physical strength and durability, key performance characteristic in demanding aerospace environments. For most other applications, calcium carbonates are the primary fillers. These are typically available as ground or marble dust or in a participated form. Lower cost sealants tend to use mostly marble dust due to its affordability. However, a portion of precipitated calcium carbonate is often included to improve thixotropy. This is to help the compound maintain its shape during application while still being easy to apply. In insulating glass sealants, a small amount of titanium dioxide is added to whiten the base formulation, while a touch of carbon black is typically included in the catalyst side to provide color balance. Calcinated dyes are consistently incorporated in building sealants. Their purpose is to help neutralize the alkalinity introduced by calcium carbonate fillers, thus enhancing long-term stability and compatibility within the formulations. Lastly, lithophone and zinc sulfide have been explored as alternatives to titanium dioxides. These fillers can provide similar pigmentation properties in applications where brightness or whiteness is desired but may be selected based on cost, availability, or formulation compatibility. Fillers not only adjust color and consistency, but also significantly influence mechanical properties, processability, and durability of the final sealant. Let's now explore the role of plasticizers, adhesion additives, and primers in polysulfide compounding. In earlier formulations, chlorinated diphenyl were commonly used as plasticizers in polysulfide sealants. However, due to environmental and toxicity concerns, they have been largely replaced by phthalates, phosphates, and glycolate esters, which offer safer and more sustainable alternatives. Toluene is occasionally used in small amounts to enhance extrusion properties, making the material easier to apply. However, its usage is minimized to reduce the VOC emissions and avoid volatility-related issues. Specifically, insulating glass sealants require low volatility plasticizers to prevent fogging within the sealed unit, fogging being a major concern in double glaze systems. Adhesion additives are critical for ensuring that the sealant bonds effectively to the substrate. In two-part building sealants, selected phenolic resins such as methylone AP108 from General Electric have proven particularly effective in promoting durable adhesions. In one-part sealant, a sealant monomer is used to provide chemical bonding to inorganic substrate. For aircraft sealants, where chemical resistance is essential, a more fuel-resistant phenolic resins such as Durez 10694 from Occidental Chemical Corporation is preferred. While most building sealants already included adhesion additives, these alone may not suffice, especially in difficult substrates. For bare metals, a diluted sealant-based primer is often necessary to improve adhesion. For porous surfaces, a film-forming primer is applied to block moisture migration at the interface, which can compromise adhesion over time. Primers can also serve as barriers against gas permeation through the substrate. For unusual or difficult building surfaces, manufacturers often offer specialized primers tailored to the specific sealant systems. Masonry primers, for instance, may contain chlorinated rubber, modified phenolic resins, and plasticizers. These are designed for compatibility with the sealants, and they are typically supplied by the sealant manufacturers. Finally, low solid sealant primers provide monomolecular films that are highly effective in promoting adhesion to metals, glass, and ceramics, making them indispensable in many architectural and industrial applications. Now this is time to end this session, and I hope you enjoy. Stay tuned for the next slides on this fascinating topic. Thank you.